Here we go with example number 1. It's discuss the concavity, which means just tell me where it's concave up or down and determine the points of inflection. So to determine the points of inflection, you have to figure out the concavity anyhow. So this is all based off the second derivative. This derivative is going to be a process because the first derivative is a product and chain rule. The second derivative will probably be the same. I'm going right to Wolfram alpha because I don't want to spend time on that. There I am. Second derivative of, I forgot what it was. So x times the square root of 9 minus x, x square root 9 minus x, and that equals, look at this, make sure we typed it in right. We did, and it equals this. So I'm going to take that and transfer it over here. That's our second derivative. That was a quick way to get by the first and second derivative. So now we have to figure out the possible points of inflection. So possible points of inflection, according to this second derivative, are where the top equals 0 and where it's undefined, where the bottom equals 0. On questions like this, as you already know, you have to make sure that these are defined in the original function, and the original function is the square root, and you can't take the square root of a negative number. So the 9 minus x part has to be positive. If you think about it, that means that x has to be 9 and below, because anything bigger than 9, like 9 minus 10, is negative, 9 minus 11 is negative. But the 10 is even too far. 9.1 would be negative in there. So the domain of this function is everything less than 9, but including 9, because you can take the square root of a negative number. So that's the domain. This point of inflection right here is not in the domain, so it's not going to be a point of inflection. X equals 9 is the only real possible point of inflection. Now, the other quick way to solve this, and I went through this domain, is the radicand 9 minus x. You can just state that 9 minus x, for the square root to be legitimate, must be greater than or equal to 0. You can't take the square root of a negative number. And now you just solve for x. Bring the negative x over. So that says x is less than or equal to 9, which is what we just said here. So anyhow, that's the setup of this problem. It's a long setup. It's something to think about, but it's going to make the problem very simple. When we make up our chart for concavity and the points of inflection, usually we're dealing with this big number line. We're going to plot our possible points of inflection and start with the charts. But we have to remember here that our domain, this graph only exists from negative infinity to 9. So this part of the chart is not even there. Graph's not there. So we're going to figure out a test number. The best one in here is 0. Plug in 0 into the second derivative. And if you look at the second derivative, you plug in 0 to the top, you're going to get 3 times a negative number, so negative. If you plug in 0 to the bottom, you'll get 9 to the 3 has, which is positive. So you're going to get a negative divided by a positive, which is a negative, which means we're concave down on the interval negative infinity to 9. It also means that there's no point of inflection, because a point of inflection is where the concavity changes in a graph. On this graph, the concavity never changes. It's always concave down. So to check that out real quick, go to Desmos or your graphing calculator and type in the original function. I did that for you here. So I typed in the function y equals x times 9 minus x. You can see from Desmos that the graph is always concave down. And also the domain is from negative infinity to 9, because after 9, the graph doesn't exist. So that's a good check on this. And it's a very interesting problem. That was the example number 1. The next video will show example number 2. It's a trig one. So I'll see you then.